Hello, welcome friends. Last time I have discussed something about the physical meaning of the operators that we use in physics. This time I am introducing a new concept. I mean, that is not new, but I think the understanding of this concept is much lower. So I just choose this. The topic is dielectrics or insulators. So the first of all, what do you mean by dielectric? Okay, dielectric, like those materials which don't have free electrons, like they have almost the electronic configuration of they have almost closed shells, or they have closed shells, electronic shells. Okay, so they have basically no free electrons. Now the dielectrics, they have many interesting properties, and I will tell you one by one. It's like properties of polarization, that is electric polarization, dispersion and absorption, ferroelectric phase transition, there are etc. many other properties dielectrics have. So how the dispersion concept has been introduced, absorption, polarization, I will tell you one by one. Before that, I just want to explain you that what happens when we apply an electric field to a dielectric material. The dielectric may be gas, the dielectric may be solid, the dielectric may be liquid. Okay, so whenever I apply a static electric field, forget about dynamic electric field, that electric field is not varying with frequency. I just apply a static electric field and I have a dielectric material. So dielectric material, basically they have bound electrons, that is they have positive charges and equal amount of negative charges, and if they without an external electric field, the center of positive charges, if the molecules are not polar, the atoms or molecules are not polar, the center of positive charge exactly coincide with the center of negative charge, resulting no dipole moment. But whenever I apply an electric field, the center of positive charge get displaced with respect to the center of negative charge, means the positive charge displacement quite lower than the negative charge displacement, because the electrons are much more lighter than nucleus. So the displacement of the nuclei will be smaller, the displacement of the electronic cloud will be higher, but overall there will be a displacement, that is there will be some kind of, if this is a spherically symmetric, after applying electric field I get the distribution like this, where the center of positive charge and center of negative charge displaced with an amount x. So there will be a net dipole, there will be a dipole moment which will be E into x. Okay, so whenever you apply an electric field to a dielectric material, the dipole moments will be generated inside the dielectric. So the dipole moments will give a polarization, that is polarization is the dipole moment per unit volume. Okay, so into n, the number of molecules per unit volume, that is polarization equals to n into p. Now we know the relationships, that is whenever the electric field is much lower, I mean I am applying this electric field, the electric field will further generate dipole moment. The more the dipole moments, the more will be the polarization. So there are kind of linear relationship between polarization and electric field, I mean sorry, dipole moment and electric field, and this relation is dipole moment equals to epsilon naught alpha into E local, because dipole moment is proportional to the electric field that I applied. Now for this proportionality constant, I introduce a new quantity alpha, that is called polarizability. This is a very important concept in physics. What do you mean by polarizability? Polarizability determines that my applied electric field, how many dipoles can be generated. That is a measurement that is atomic polarizability can give us. And next, I have also told you that polarization, dipole moment is P, and polarization is, macroscopic polarization is N into P, where N is the number of atoms or molecules per unit volume. So for this, my polarization is also linearly proportional to the external electric field I have applied, and here I introduce the proportionality constant epsilon naught chi e. So this is called the electric susceptibility. Rather it was electric polarizability, this is electric susceptibility. The susceptibility, what do you mean by susceptibility? Susceptibility means that the degree of polarization, the applied electric field, how much polarization it can generate, a material can generate by this applied electric field. It depends on the properties of the materials. The polarizability, susceptibility all depends on the properties of the dielectric material. Okay. Now we know the linear relationship. So let me first erase it. We know the displacement vector D equals to epsilon naught E plus P. From there I just put the value of P which I have introduced, and let us forget this side, this is for another thing, I will tell you later. The polarizations, dipole moment, the polarization and the displacement vector, and I put the values and I get displacement equals to epsilon naught epsilon r epsilon e, where epsilon r is the relative permittivity or dielectric constant. This epsilon r is 1 plus susceptibility equals to n into alpha. This is the Clausius relation, where the dielectric constant is related to the susceptibility or related to the polarizability. Look at the equation. Whenever you see an equation, you have to understand that the dielectric constant is the property of this material which is coming from the susceptibility or the polarizability, because how much polarization, how much dipole moment will be created, that will determine the amount of polarization. Much more polarization means much more dielectric constant. Okay, that is the basic thing which you can understand from this equation. Now epsilon r equals to this relation equals to 1 plus chi e equals to n alpha. This relation is applicable for the gaseous dielectric, where I have assumed that the dipoles are not the electrons are realizing the electric field, how much it has been applied, the electric field which is exactly applied, that is the electrons are applying the same electric field which I have applied. But in gaseous molecule the assumption is quite correct. Okay, that the electric field is applied, the realized by the same amount by the electrons, and they get displaced, and then we get dipoles, and from that we get polarization and we get dielectric constant. Now in case of solid or liquid, this is not the case, because in solid and liquid the you have a charge distribution, nuclei charge distribution and electronic charge distribution. I told you there is some displacement of this nucleus with the electrons, and you know in liquid solids there are much more dipoles within a very short distance. So the electric field that I have applied, it is not exactly the same that the electron here will realize. The local electric field will be quite different from the applied electric field. So here in this case E local is not equals to E applied. Okay, rather whenever you have some kind of bulk dielectric material, here we get negative positive dipole moment, positive charges separated. Now you have applied this electric field, this is my applied electric field. Now due to this applied electric field, there will be internally generated depolarizing field which will try to depolarize these molecules, depolarize the dipoles. Okay, this is the E depolarizing field, this is the internal field. It will come to play to oppose the applied electric field. Okay, and another thing is that here also I will get the dipole-dipole interaction, the interaction between interaction on one dipole due to the surrounding dipoles. So overall I want to say that the E local that is experienced by one electron is not same as the E field that I have applied or that anyone has applied. So the electric field here, last time I have taken that the electric P, that is small p, equals to epsilon naught alpha into E. That E was the same as the E applied, but in this case, in this solid or liquid, the P, the dipole moment that has been induced, it is not the E applied, it will be proportional to the E local. Okay, and E local for Lorentz has been calculated for spherical distribution. E local will be E internal plus P by epsilon naught, where EM I have written is EM as E applied plus E depolarizing field, and this P by 3 epsilon naught is the dipole-dipole interaction term for spherical distribution. I have calculated as P by 3 epsilon naught. I mean, overall the dielectric constant will be epsilon naught E plus epsilon naught N naught alpha into EM, where EM term comes from the E applied field plus E depolarizing field, plus another terms come from the dipole-dipole interaction term. I have calculated, or Lorentz has calculated this, so I have put this value for the spherical distribution, P by 3 epsilon naught. So the dielectric constant value, that is epsilon r, earlier it will be changed, the epsilon r minus 1 by epsilon r plus 2 equals to N alpha by 3. Earlier it was epsilon r minus 1 equals to N into alpha. It has been changed for the solid and liquid dielectrics. This is valid for gaseous dielectric, and it has been changed due to this E local, the electric field realized by the local electric field applied on the electrons. Okay, so this is the Clausius-Mosotti relation for the dielectric constant of a solid or liquid dielectrics. Now if I am telling you, when the electric field is static, okay, I have applied a static electric field, and you know there will be the charge separation, the center of positive charges will and the center of negative charges will get displaced, and we get a dipole moment. Okay, and the dipole moment, the dielectric constant I will get is not frequency dependent, it is static dielectric constant. But what happens if we apply the incident electric field, time varying incident electric field, like we apply light, that is the electric field frequency is electric field is frequency dependent, or we apply AC current. What will happen at the time? What will happen to the dielectric constant? The dielectric constant will also be frequency dependent. Okay, before that okay, first of all, okay, it's okay, I just explain it, then I come to another concept. Okay, so whenever you apply electric field, frequency dependent electric field, the electrons will move. I mean, the electrons will also oscillate with this due to this frequency variation of the incident electric field. So the equation of motion of the electron will be m d2x d2. Let us take the displacement is x, the displacement x, m d2x dt2 plus q is a damping factor of dx dt plus omega naught square x equals to the applied electric field. This is a motion of a forced vibration. The electron is doing a forced vibration motion under the frequency of that incident electric field. Okay, so displacement will, I can write it x equals to x naught e to the power I omega t, and we know that dipole moment is minus e, is the electronic charge minus e into the displacement x naught. So we get polarization is n e square by m e naught by omega naught square minus omega square plus I q omega. Okay, here the polarization is complex quantity. You are saying that this is a real part and it has some imaginary part. Now we know that polarization equals to epsilon naught chi e. Chi is the susceptibility. Now chi can be written as epsilon minus 1. So epsilon is the dielectric constant. So here you can understand that the epsilon is also dependent on frequency, because the dependent on P is also dependent on frequency. Polarization is also dipole moment dependent on frequency. Hence the polarization is also dependent on frequency. Hence the dielectric constant is also dependent on frequency, and it is not only real but it has a imaginary part. So dielectric constant, which is a frequency function of frequency, it has some real part plus it has some imaginary part. Now what the real part of the dielectric constant represent, what the imaginary part of the dielectric constant represent. The real part of dielectric constant tells you the change in the refractive index, because refractive index equals to real part of the dielectric constant whole square. Okay, this is the refractive index. The refractive index equals to dielectric constant whole square, and this dielectric constant is the real part of this dielectric constant. Now refractive index, whenever the dielectric constant is varying, so the real part of the dielectric constant will also vary. The real part of the dielectric constant correspond to the refractive index, so the change in real part of the dielectric constant correspond to the change in the refractive index. So change in the refractive index with frequency means dispersion. So here the concept of dispersion has been introduced, that the change of refractive index with frequency, that is called dispersion, that belongs to the real part of the dielectric constant, and the imaginary part tells you the absorption. So basically this is the physics of dielectric constant, that you will get two parts, real and imaginary, where the real part gives you the concept of dispersion, the physics of dispersion, and the imaginary part tells you the absorption or dissipation of energy. Now I am telling you another thing, that is atomic polarizability. Last time I told you that dipole moment is equals to epsilon naught into alpha into E, where E is much lower. The linear variation I have taken. For E to be higher, the polarizability will be a tensor and it will be non-linear. The only E term nahi, not only the E term, E square and other higher terms should be included. Okay. Now when the applied field, electric field is much lower, then dipole moments can be directly proportional to the applied electric field. Now this is the polarizability, which what I want to tell you, that there are three different polarizabilities exist. One is the electronic polarizability, another is the ionic polarizability, and the last one is the orientational polarizability. Now what do you mean by electronic polarizability? What do you mean by ionic polarizability? What do you mean by orientational polarizability? Electronic polarizability happens when the displacement, whenever you are applying a electric field, the electrons are much lighter. Okay, with the variation of the applying electric field, the electron can respond and it will oscillate. It can oscillate with that incident electric field. Okay, so therefore the net displacement of the electronic charges happen, which further introduce dipole moments and which will enhance the polarization, and from that our dielectric constant we can get, it will be further increased. Okay, now the electronic polarization is the displacement of electrons to generate the polarization. Now ionic polarization, similarly, the displacement of ions which will contribute to the polarization. Suppose NaCl, sodium chloride, here sodium chloride, Na sodium ion and chlorine ions, so Na plus and Cl minus ions they are existing in their cubic lattice structure. You are applying the electric field and the displacement of the ions will further contribute to the polarization. So it is the ionic polarizability. And what happened to the orientation in case of orientational polarizability? Orientation, suppose we are taking a polar molecule like H2O. Okay, H2O, here this is the H, this is O, this is H and H, and here I think the angle is 106 degree nearly or whatever. So here already there are inherent dipole moments. I mean, without introducing any external electric field, the molecules are polar. Okay, so there are polar molecules there, they have some intrinsic P without E applied. So what happened when you apply electric field to this polar molecules? Whenever you apply electric field, the orientation of the dipoles will be such that they will try to orient along the externally applied electric field to enhance or to give polarization. So whenever you apply electric field to a polar molecule, the dipoles will be oriented so that along the electric field. Okay, but this is called the orientational polarizability. It will contribute to the polarization. Now with this, the orientation of the dipoles with this applied electric field, there are another thing, that is thermal energy within that material, within that molecule, which will try to de-align the alignment. They will try to oppose the alignment of the dipoles. So this will be the polarization. P average will be a statistical average of dipoles, and it will be temperature dependent, and it will be proportional to, after calculating you will get this, it will be proportional to 1 by T. That is, the temperature will be lower, the polarizability will be higher, and the temperature will be higher, the orientational polarizability will be lower. Okay. So the three polarizability that can contribute to the overall polarization. Now what happens, I have written here that the electronic polarizability contribute in the ultraviolet, ionic polarizability is infrared, and orientational polarizability in microwave. This means at this frequency the orientational polarizability will come to play. At infrared frequency, the ionic polarizability will come to play. It is not come when the frequency will be higher, because the ions are much more massive than electrons. For a rapidly varying electric field, the ions cannot respond it, right, because they cannot oscillate with a rapidly applied electric field. So the polarizability due to the ions, due to the displacement of ions, will contribute only when the frequency is much lower. So that is the infrared frequency. But electrons can much more respond rapidly to a rapidly varying electric field. So electronic polarizability contribute to the ultraviolet region. Okay. Now for some materials you will see that the dielectric constant for higher frequency will be lower. Higher frequency means suppose the optical frequency will be lower than whatever it was